Assalamu alaikum. My name is Maqsood and I am a student of EA University Islamabad and I am currently doing mechatronics engineering. So today I am here to show you my lab task 13 of microcontroller and embedded system lab. So which was based on FPGA. So this lab was basically, as I told you before in lab 10, 11 and 12, that what is an FPGA, what is Quartus, Modasim Altera, what are these software, and I will give a short introduction about it here too. So basically, what is an FPGA? FPGA is an integrated circuit designed to be configured by a customer or designer after manufacturing, hence the term field programmable. So basically, in short terms, it is a gate array, a complex gate arrays. It is based on complex gate array and it is much more efficient than microcontrollers. Basically everything and every architecture, 7 segment display, USB port, everything is already installed on this device already. So basically it is much more efficient and much more costly than other microcontrollers as well. So about Quartus, so basically what is a Quartus? Quartus is a programmable logic device. Intel Quartus Prime is a programmable logic device design software produced by Intel prior to Intel's acquisition of Altera, the tool that was called Altera Quartus Prime. So before Quartus, we had to do work on Model Sim Altera, which was another software for this, and we have to do a Verilog HDL coding in our Quartus Prime. So basically, I've downloaded the version Quartus 13, and Quartus Prime enables analysis and synthesis of HDL designs, and we have done our coding in Verilog HDL for our designs, which enables a developer to compile their designs, perform timing analysis, examine RTL diagrams, which we will discuss too in our code, simulate a design's reaction to different stimuli, and configure the target device with the programmer. Quartus Prime includes an implementation of VHDL and Verilog for hardware description. So that's why I have told you before that whenever we do it on, we have to perform our task on hardware form. We have done, that's why we have to do coding in Verilog HDL. So this was all for Quartus 13, and as you can see, we have done lab 12 mux and demux in lab 12 encoders and decoders. Basically what is an encoder? Is a digital signal. Basically what it does, that if many inputs are given to an encoder, so it basically encodes those values and uh, display it in 2 into n. If there are 2 into n input lines, then it will display only n bits on output lines. So basically this was all for our encoder. Basically what is a decoder? It is as a vice versa to, it works as a vice versa to encoder. If we have 2 inputs, then we will have 4 outputs. That is, if we have n inputs, then our output will be in the form of 2 cross n. And encoder, if the input was 2 cross n, 2 into power n, then the output was n. So it works vice versa, it works both ways. And I have described already mux and demux. What is a mux? That it selects among inputs and display an output. And it is a demux, that among one input it you know uh, decode it, and in the form of a single input it select one of many data line outputs. So this was all for lab 12, when we implemented it in different forms, in gate level implementation, in logic statement implementation. So now straightly coming towards our lab 13, which was based on adders and subtractors. So basically let's go to our introduction. What is an adder and subtractor? Adder and subtractor, or is a circuit that is capable of adding or subtracting numbers, in particularly binary values. This is a kind of a circuit for adder. So basically these are 1 bit full adders, and these are our inputs. So basically when A0 is an input comes, and when B0 as an input comes, and then C is defined as carry, and S0 is basically our sum. So the carry goes to other bit, then the function it performs its function, then it will display its sum. Then another carry will be added to next 1 bit full adder. It will perform its function and give us S2, and same goes in adders basically. by the fourth operation gives a sum that consists of two binary digits. In such result of the addition, the lower significant bit is called as a sum bit, whereas the higher significant bit is called carry bit, as I told you before. So basically our work was to add these we basically our work was to add we was to run these codes which was given to us. Now what is a half adder? Half adder has two inputs generally labeled as A and B, and two outputs, the sum C and carry sum S and carry C. And second type is a full bit adder. The full bit adder takes into account a carry input such that the multiple adders can be used to add large numbers. What is a ripper carry adder? When multiple full adders are used with the carry ins and carries outs chained together, then it is called ripper carry adder, because the correct value of the carry bit ripples from one bit to next bit. So basically this was all for carry adders. Now as I have already run this code in my Quartus 13, you can see it's the same code in here. So whenever I will compile my code, it will be compiled successfully. So basically it has been successfully compiled. So when I will go into my RTL viewer, as I told you before that we will check this command as well, it will kind of give us a simulation for our code as a software simulation. So basically this is a software simulation for our code. So whenever I will now check its waveforms, when I will go into new VWF University program and click on. So this was period given to my waveforms as A and B was input, and whenever I run my waveforms, it will run successfully. As it has been run successfully, a new window will appear, and as you can see, these waveforms were this A and B were our inputs, and this sum was my output. We can verify this as well. So basically this is how Quartus work, and this is how our adder circuit was working. And now going towards my lab task 2. So this was my lab task 2, which was following is the Verilog code for unsigned 4-bit adder with carry in and carry out. So basically this was my lab task 2. So now I will show you my code as well. So this was my code for lab task 2. So whenever I run my code, Control L, it will be successfully compiled. So basically it has been successfully compiled, as you can see in here. For its simulation, I will go into locate an RTL viewer. So this was kind of simulation for my adder circuit. This was sum bit, this was carry bit. So this is how it works for pin planner. For implementing it in on hardware, so we have to give pin number in here, and we have to connect pin number on hardware form as well. So this command is used for that. For checking its waveform, we have to go into new University VWF. So A, B and CI was our input. So whenever I run my waveforms, I've given them equal time period, dividing them by 2. So you will see, as you will see, it has been successfully compiled, and a new window will appear which will show our waveforms. So you will see A was our input, B was our input, CI was our input, and CO and sum was our output. So this is how Quartus 13 works, and this is how code worked in Quartus. So for other tasks as well, for this lab task 3, these lab task 3, lab task 4 and lab task 5 was given to us. So basically this is how it works in Quartus. So this is how we can add, subtract, we can use demugs, we can use mugs, we can use arithmetic operations, logical operations in our Quartus for implementing it on FPGA. Thank you so much.